Welcome to Chapter 7, the Binomial Theorem. This powerful theorem gives us an easy way to expand expressions like a plus b to the power n without doing repeated multiplication. It's based on patterns discovered by Blaise Pascal in the 17th century. The theorem makes calculating high powers practical. Let's start with simple binomial expansions. A plus b to the 0 equals 1. A plus b to the 1 equals a plus b. A plus b squared equals a squared plus 2ab plus b squared. A plus b cubed equals a cubed plus 3a squared, b plus 3ab squared plus b cubed. Notice the patterns forming. Key patterns emerge in binomial expansions. The number of terms is always one more than the index, so a plus b to the n has n plus 1 terms. Powers of a decrease by 1 in each successive term. Powers of b increase by 1, and importantly, the sum of the indices of a and b equals n in every term. Pascal's triangle is a beautiful arrangement of numbers. Each row gives the coefficients for expanding a plus b to the n. The triangle starts with 1 at the top. Each number below is the sum of the two numbers above it. Every row starts and ends with 1. This pattern continues indefinitely. We can express Pascal's triangle using combination notation. Row n contains nC0, nC1, nC2, all the way to ncn. Remember, nCr equals n factorial divided by r factorial times n minus r factorial. For example, row 5 gives us 5c0, 5c1, 5c2, 5c3, 5c4, 5c5, which equals 1, 5, 10, 10, 5, 1. The binomial theorem states a plus b to the n equals nc0 times a to the n, plus nc1 times a to the n minus 1 times b, plus nc2 times a to the n minus 2 times b squared, continuing until ncn times b to the n. The general term is t subscript r plus 1 equals ncr times a to the n minus r times b to the r. This is proven using mathematical induction. Let's expand x plus 2 to the 6. Using the theorem, 6c0 times x to the 6 plus 6c1 times x to the 5 times 2 plus 6c2 times x to the 4 times 4, and so on. This gives us x to the 6 plus 12x to the 5 plus 60x to the 4 plus 160x cubed plus 240x squared plus 192x plus 64. The binomial coefficients are 1, 6, 15, 20, 15, 6, 1. For x minus y to the n, we replace b with negative y. The expansion becomes nc0 times x to the n minus nc1 times x to the n minus times y plus nc2 times x to the n minus 2 times y squared, and so on. The signs alternate, plus minus plus minus. The sign of term r is negative 1 to the r. A special case, 1 plus x to the n. Setting a equal to 1 and b equal to x, we get nc0 plus nc1 times x plus nc2 times x squared, continuing to ncn times x to the n. For x equals 1, this gives us 2 to the n equals the sum of all binomial coefficients. This is a fundamental identity. Another special case, 1 minus x to the n. Setting a equal to 1 and b equal to negative x, we get alternating signs. For x equals 1, the alternating sum equals 0, nc0 minus nc1 plus nc2 minus equals 0. This identity is useful in many mathematical proofs. To find specific terms, use the general term formula. T subscript r plus 1 equals ncr times a to the n minus r times b to the r. The first term, t1, equals a to the n. The last term, t subscript n plus 1 equals b to the n. Middle terms depend on whether n is even or odd. To find the coefficient of x to the r in a plus bx to the n, use the general term. It's ncr times a to the n minus r times bx to the r. So the coefficient is ncr times a to the n minus r times b to the r. For example, finding the coefficient of x cubed in 1 plus 2x to the 5. Finding middle terms, if n is even, there's one middle term, t subscript n per 2 plus 1. If n is odd, there are two middle terms, t subscript n plus 1, 2, and t subscript n plus 3 verse 2. For example, a plus b to the 4 has middle term t3. A plus b to the 5 has middle terms t3 and t4. Numerical applications are powerful. To calculate 98 to the 5, write it as 100 minus 2 to the 5. Use the binomial expansion. This is much easier than direct multiplication. Another example, 1.01 to the 100 is greater than 100, which we can prove using just the first few terms. Important properties of binomial coefficients. The sum nc0 plus nc1 plus ncn equals 2 to the n. The alternating sum nc0 minus nc1 plus nc2 minus equals 0. Symmetry. nck equals ncn minus k. These properties follow from setting x equal to 1 or x equal to negative 1 in special cases. The greatest binomial coefficient depends on n. For n even, NCn2 is the greatest. For n odd, NCn-1, 2, and NCn+1, 2 are equal and greatest. The coefficients increase to the middle, then decrease symmetrically. This pattern is visible in Pascal's triangle. The binomial theorem helps prove divisibility. For example, proving 6 to the n-5n leaves remainder 1 when divided by 25. Write 6 to the n as 1 plus 5 to the n. Expand using the binomial theorem. Extract terms divisible by 25. The remainder is indeed 1. Approximations use the binomial theorem. For small x, 1 plus x to the n is approximately 1 plus nx. The first two terms are often sufficient for good approximations. This is used throughout physics and engineering. For example, 1.01 to the 100 is approximately 1 plus 100 times 0.01, which equals 2. Watch out for common mistakes. Don't forget the alternating signs in x minus y to the n. When finding a specific term, be careful with the term number. The rth term uses nCr-1. Simplify coefficients properly. Remember, the coefficient is just the number, not including the variables. Key formulas to remember. A plus b to the n equals the sum from r equals 0 to n of nCr times a to the n minus r times b to the r. The general term is t subscript r plus 1 equals nCr times a to the n minus r times b to the r. The sum of all coefficients equals 2 to the n. The alternating sum equals 0. Problem-solving strategy. First, identify which form you have, a plus b to the n, a minus b to the n, or 1 plus x to the n. Determine which term you need. Apply the general term formula. Simplify carefully, watching for signs and powers. Let's find the fifth term in 2x plus 3 to the 7. t5 equals t subscript 4 plus 1, so r equals 4. Using the formula, 7c4 times 2x to the 7 minus 4 times 3 to the 4. That's 7c4 times 2x cubed times 81. Calculate. 35 times 8x cubed times 81 equals 2260 or x cubed. Find the coefficient of x to the 10 in x squared plus 1x to the 20. The general term is t subscript, r plus 1, equals 20cr times x squared to the 20 minus r times 1x to the r. Simplifying, 20cr times x to the 40 minus 2r times x to the minus r equals 20cr times x to the 40 minus 3r. For x to the 10, 40 minus 3r equals 10, so r equals 10. The coefficient is 20c10. The binomial theorem connects to probability through the binomial distribution. The probability of exactly r successes in n independent trials is p of r equals nCr times p to the r times 1 minus p to the n minus r. The binomial coefficients are fundamental to probability theory. This is one of the most important distributions in statistics. In this chapter, we learned that the binomial theorem efficiently expands a plus b to the n. Pascal's triangle provides the coefficients visually. The general term is t subscript r plus 1 equals nCr times a to the n minus r times b to the r. Special cases like 1 plus x to the n simplify many problems. Applications range from approximations to divisibility proofs. Thank you for joining Chapter 7 on the binomial theorem.